Welcome to the course on biostatistics and design of experiments. We will talk about hypergeometric and log normal distributions. Yesterday I introduced hypergeometric, let me continue on that. So, hypergeometric is a distribution which looks at situations where the population is not very large, that means the sample size are almost in the ballpark figure of population, unlike a normal distribution where the population is very large, almost infinite. So, here the sample also is reasonably large comparable to the population, and the probability distribution is given by this C as x, Cn minus x by n minus small x, Cn n, where capital N is the population, n is the sample size, okay. X is the number of successes in the trial, okay. S is the maximum possible number of successes, and this is called the probability of observing x successes, okay. So, the mean is given by mu into S small n by capital N, n is your sample size, capital N is the population size, S is the possible number of successes, that is the maximum that is possible, and the variance is given in this formula S n minus S multiplied by n capital N minus small n divided by n square n minus 1, okay. So, this is the variance and this is the mean of this particular distribution, which is called the hypergeometric distribution. So, as I said here, the sample size is reasonably very close and comparable to the population, unlike the normal, okay. So, it is a discrete distribution because we are taking sample is done without replacement, okay. So, you take it out and there is no replacement. N is a finite and known, each trial has exactly two possible outcomes, success or failure, okay. Suppose I pick up balls from bag which may have a black or white, okay. So, success, failure, black, white, yes, no. The trials are not independent, x is the number of successes in the n trials, okay. Let us look at a problem. So, it arises because of sampling from a fixed population. So, imagine there are 50 colonies, okay, which has 5 mutants. So, 45 of them are normal, okay. Now, I have removed 10 colonies from this lot, and imagine there are exactly 4 mutants out of this 10. So, 6 of them are normal. So, we have drawn 10, okay, we have drawn 10, 4 of them are mutant, normal is 6, okay. Total has 5 mutants and 45 normal, the total is 50, okay. So, we cannot exactly model by binomial because the probability of success on each trial is not the same, because we are removing it and we are not replacing them, okay. Unlike a coin, no, we toss heads or tails, then again we toss the coin. So, probability is again heads or tails is 0.5 and so on, okay. So, whereas in this case we have removed it and we are not replacing it. So, the probability keeps changing. So, in such situation you think about hypergeometric distribution. Do you understand the difference, okay. Now, because when you remove, for example, these balls or these mutants, what is remaining changes, keep changing, okay. So, the probability of that keeps changing, okay. So, the probability of drawing exactly 4 black balls or 4 mutants in this particular example can be calculated from that formula. What is this formula? C S x, okay, into C n minus s d of n minus x, C of n small n, okay. So, we just what we have got here in this particular thing is we have got 4 successes in a sample of 10, the maximum successes possible is 5 in capital N of 50. So, capital N is 50, small n is 10, capital S is 5, small x is 4, okay. So, we can substitute in our equation. So, we have okay, C 5 4, C 45 6, okay. 4 is the mutants you took out from the 10. So, the remaining is 6 here. So, what is C 5 4? If you remember the factorial, this is factorial 5 divided by 4 factorial divided by 5 minus 4 factorial, this one is 45 factorial divided by 6 factorial divided by 39 factorial, this is 50 factorial divided by 10 factorial divided by 40 factorial. So, if you do this C54 will come out to be 5, and this particular 45 factorial divided by 6 factorial divided by 39 factorial will come out to be this, and this will come out to be this. So, you end up having a probability of 0.0039. Okay, what is the probability of getting all 5 as say black or mutant? So, the remaining 5 in that sample of 10 will be normal. So, what we do, we put here 5, this will 6 will become 5, okay, other things will remain same. So, when you do that, of course, C55 is 1, if you remember from our olden days. So, we get out a probability very small, 0.00011. So, this is as expected. If you want to take out all the 5 mutants, okay, when you take a sample of 10, obviously it is much larger than taking out 4 mutants in a sample of 10. Okay, now we can also do it by Excel. There is a function, hypergeometric distribution, okay. In that we have sample, okay, successes, number of samples. So, this will be like x, this will be like small n, this will be like your capital S, and this will be like your capital N. Do you understand? Okay, this is like your x, this will be like small n, this will be like your capital S, this will be like your capital N. Okay, let us look at it for this particular problem situation. Okay, using this particular Excel piece. Let me first get out my Excel out of this. Okay, so we do Excel. Okay, so we say hypergeometric distribution, DIS. So, this is like we are getting 4 mutants or 4 black ball in a sample of 10. The maximum that is possible is 5. The capital N is 50. So, we substitute and then we should get 0.0039. Okay. So, it has got a probability of 0.0039. So, if all 5 needs to be black or mutant, same thing we can do MDIST, okay, 5 comma out of 10, 5 out of 50, right, 0.30119. So, sorry, 0.30119. Okay. So, we can use Excel also to do the same thing. Okay. It is quite simple with the Excel. As you can see here, we give the number of successes in a sample, and this is the maximum number of successes possible, and this is the population, okay, number. Okay, we cannot use binomial, as I said, we are taking out and we are not replacing. So, obviously, the probability may keep changing as you keep drawing mutants. Okay, let us look at another problem. Okay, so, there are 80 significant genes from a microarray experiments of yeast, and it has got a 6000 genes. Okay, we have taken 80 significant genes. Now, 10 of these 80 are in BP-GO term, that is DNA replication. Okay, but total number of these genes in GO term is 100. So, what is the probability of this GO occurrence by this chance? Okay. So, 6000 genes, maximum possible is 100, okay, maximum possible is 100. When we took out 80 in that list, we find 10, okay. So, we will call it 10 successes out of 80, the maximum possible is 100. So, capital N is 6000. So, here small n is 80, x is 10, okay, small n is 80, x is 10, and the maximum, that is capital S, is 100. Okay. So, we can get the probability. So, hypergeometric distribution, quite straightforward. This is GEO MDIST. Okay. So, the what we got is 10, in a list when we took out 80, but maximum possible is 100 out of 6000. Okay. So, we get 5.9 into 10 power minus 7, understand. So, it is quite straightforward using the Excel, but this distribution is useful where we cannot use binomial, but this also has like yes no, live dead and that sort of situations we can use actually. So, we can use in problems where we actually do not know the situations, unlike okay, we do not, for example, let us take n laboratory mice, n of them small n are male. So, n minus n are females. Now, we do a certain mutation after radiation. So, now there are m new mutant mice, okay. You do not know whether in this m how many males are mutants and how many females are mutant, okay. That is the problem, okay. Then how do we do this actually? Okay, so there is something called Fisher's exact test, which cannot break it down, but it can give you a total probability of this actually. Let us look at one problem. So, there is a 2 by 2 table. Of course, 2 by 2 table contingency we used to use chi-square, but here we are going to use Fisher table, okay. This Fisher's exact test, it does not do a test statistics and there is no critical value, but it gives you only a p value for observing this type of numbers, okay. So, for different types of tables it just gives you what is the probability, okay. So, let us look at an example. So, there is a HIV infection and there is a sexually transmitted in this, that is the history of sexual transmission in sub-Sahara African country. So, S for history of sexually transmitted disease, no, and HIV infection S and no. So, we find that there are 3 cases where there is a history of STD and also HIV infection. There is a history of STD, but no HIV infection is this much. There is no history of STD, but there is HIV infection. There is no history of STD and there is no HIV infection. So, you have this data, you can find out what is the probability of getting this type of table, okay. So, this Fisher's exact test gives you that sort of numbers. It does not have a test statistics, it does not give you a critical value and comparison and p value and so on actually. So, how do we go about doing this? So, we look at it as a hypergeometric distribution, okay. This is an hypergeometric distribution. So, we look at different factorials of creating this type of numbers, okay. So, we can have here 3, if you have 2 then this will become 8, okay, and you can have 1 then this will become 9, or if you have 0 this can become entirely 10 also, okay. So, we will look at each one of them. Okay, so probability of 3, 7, 5, 10, okay, 3, 7, 5, 10 is given by 10 factorial, 15 factorial, 8 factorial, 17 factorial, okay. What is that? 10 factorial, 15 factorial, 8 factorial, 17 factorial divided by 25 factorial, okay, 25 is the total, 3 factorial, 7 factorial, 5 factorial, 10 factorial, okay. So, that gives you a probability of 0.3332, understand. So, the probability of seeing this type of contingency table, okay, with 3, 7, 5, 10 is this much. So, similarly we can do for just like 3 we can do for 2. 2 means as I said, if it is 2 this will become okay, this will become 8 here, okay, okay. If it is 2 this will become 8 and this will become 6 because the total you are maintaining. So, if this becomes 2 VSS then obviously this will become 6, and if it is 2 SS then obviously this will become 8, okay. So, again use the same approach for a 2869 we do 10 factorial, 15 factorial, 8 factorial, 17 factorial, that is these numbers divided by 25 factorial, 2 factorial, 8 factorial, 6 factorial, 9 factorial, that is a probability of 0.208. and for a 1978, that means if we put 1, okay, if I put 1 here, this will become 9, if I put 1 here, this will become 7. For a 1978, then that probability is given by 10 factorial 15 8 17. These are the row sums and column sums divided by 25 factorial, that is the grand total, then 1978, that gives you a probability of 0.0595. So, if you want to see 0 10 8 7, that is 0 10 8 7 means here 0, so then this will become 10, this will become 8. Okay, so for a 0 10 8 7, again 10 factorial 15 8 17 divided by 25 0 10 8 7, that gives you a probability of 0.0059. So, a probability of finding this sort of 3 7 5 10 is given like this, probability of finding 2 8 6 7 6 9 is given like this, probability of finding 1978 is given like this, probability of finding this is given like this actually. Do you understand? So, this Fisher's exact test is used in situations where there is no test statistics. Okay. We cannot use a chi-square, but it gives you a probability value here. Okay. So, there is no test statistics, there is no critical value, but it tells you what is the probability of observing this type of table. Okay. So, you see that the hypergeometric is useful in this type of situations where the n, capital N is known, unlike the normal distribution, and your small n is comparable to capital N. Okay. The small n is the sample size. Okay, let us look at another distribution, that is called log normal distribution. So, it is a logarithmic of normal distribution. So, it is not uniform, it is defined in this form. A random variable x is said to have a log normal distribution if it looks like this. You can see it almost looks like your normal curve, but you have ln x there. Okay, for x greater than 0, okay, if it is it is 0 for x less than 0. Okay, so sometimes it is called anti-log normal distribution because the distribution of the random variable x. It is also called Cobb-Douglas distribution if you are analyzing economic data. Okay. The probability density function, distribution function, okay, for the log normal. So, the mean is given by E mu plus sigma square by 2, mu is your okay, mean, and sigma is your, and then variance is given by E 2 mu E sigma square E sigma square minus 1, and the median, that is at the 50% point, is given by E raised to the power mu. The cumulative distribution function is given like this, n logarithm of x minus mu by sigma. Okay, now this distribution is unimodal and the mode is given by E mu minus sigma square. Okay. But it is not symmetric, as you can see here, it is not symmetric. Okay. And this is the mode, mode is E mu minus sigma square and the median is E mu. Okay. So, obviously median is greater than mode. Okay. And this is how the graphs will look like, the normal distribution. Okay. So, Excel also has a command log norm dist, where you give x is the value at which you want to evaluate the function, mean is the mean of logarithm x, this is the standard deviation of this log normal distribution. Do you understand? So, we give at which where you want to find, where the mean is given, standard deviation is given. You can look at a problem which can give you some idea about it. So, ductile strength of some biomaterials follow log normal distribution, mu is 5 and sigma is 0.5. Compute the E and the variance. What is E? Mean, E mu plus sigma square by 2, right. So, how do you calculate? Very simple, E mu plus sigma square by 2. So, mu is given by 0.5, I mean sorry 5 and sigma is 0.1. So, square it divided by 2. So, the mean is given by this. Variance, what is the formula for variance? Variance is given like this, right, E raised to the power 2 mu E sigma square minus 1. So, we calculate that and we get a variance of 223. Now, the question is third, compute the probability that the data will lie between 110 and 130. Okay. So, okay, 110 and 130. Before that, sorry, before that this compute that the what is the probability for x greater than 120. Okay, so what do? We calculate 1 minus x less than 120, you all remember that, right? And then we calculate the z. If you remember our old z, how do you calculate? X minus mu by sigma, right? X minus mu, here we take logarithm x, right, 120 for x means logarithm x, mu is given by 5, sigma is 0.1, so we get 2.13. Okay, so we go to, remember our old is a table, 2.13, okay, 0.0166, 0.0166. You remember our old z table, so it is 0.0166, 1 minus 0.0166 is 0.983. So, the probability of having x greater than 120 is 0.9833. So, here we have to use the z table, but here remember x minus mu by sigma is our z, but here we take the logarithm of x, that is the only difference. Now, how do we do this part? Compute for probability for x lying between 110 and 130. This is like just like our z calculation, you remember long time back we did that. Only thing is instead of x we use logarithm x. Okay. So, how do you do this for x between 110 and 130? So, we take logarithm of 110, we take logarithm of 130, mu is 5, sigma is 0.1. So, when we calculate this it comes out to be 2.99, 1.32. So, go to our z table, 2.99 is 0.0014, okay, 0.0014, and 1.32 is given by 1.32. Remember this is our z table, 0.0934, this is our z table if you remember, 0.0934. So, we subtract, we end up with 0.092. So, the probability of having between 110 and 130 of x is 0.092. Median, the question is here, what is the value of the median ductile strength? As you know, median, we have that equation e raised to the power mu, simple. So, what we do, e raised to the power mu is given by 5, so that gives you 148.41. So, you see all these calculations can be done, instead of x we use ln x. So, we calculate z and then we go to our z table and start getting the probability value. So, it is like that standardized normal distribution. Okay. So, the log normal distribution is also a useful type of function, okay, and you have the Excel command also for log normal distribution, which also plays a very important role, as I showed you in an example related to biomaterial. Okay. So, we looked at different types of distributions over the past 3 or 4 lectures, the Weibull distribution, apart from our the F distribution, T distribution, normal distribution, binomial, then the Poisson, we looked at things like Weibull distribution, like the beta distribution, then log normal distribution, okay, hypergeometric distribution. So, all these are very useful distributions to have. As you can see, many of them are ordinal type of data, and in some situations where we cannot use a chi-square test, then we may have to use these type of distributions and tests for our calculations. Okay. Thank you very much. We will continue further.